Oh, hello. Welcome to a second lecture on the applications of machine learning models and algorithms. And today we'll continue with the decision trees, and in particular, the card algorithm as implemented in the rpart library in R. So let me share the screen and go to our presentation. What we're going to do today is basically look at the famous Boston database or data frame in R that is in MES library. But because we're first are exploring the applications of decision trees as they pertain to applications with class variables or qualitative variable, categorical variables, the class variables, what they call in machine learning language. So another common name is the features, and each feature is going to have classes. So the very first thing that we're going to do, since we're talking about the application of machine learning algorithms, and we're going to be using the when we apply the models, we're going to be looking at the method called class. So that's basically, we're looking at factor variables and class variables. So for that purpose, I'm taking all of the 13 variables that are contained, except I guess the outcome variable, which is again the median price of a house. And I'm going to convert them into factor level variables with 4 levels or 4 quantile values, which are called the quartiles. So it's the 25th percentile, 50th percentile, 75th percentile that separate these values for the quartile ranges of data within which the data falls in. So we'll have the first bucket, second bucket, and the third quartile, and the fourth quartile of data with the specific ranges, as opposed to treating the variable as linear and continuous, or so-called continuous variable, because in mathematics, the notion of continuity is very specific, and it deals with the limits of functions and the way that you approach the limits, from either direction of a function. And if the limit exists and is the same, we say that the function or the data are continuous at that particular location. So we have a little bit different notion in applied disciplines of what continuity really means, but it means basically infinite number of decimals between the units of measurement. Loosely speaking, that's a very imprecise definition. So how are we going to split the data into the respective levels? And for that purpose, we're going to be using a syntax from so-called GTools library. And the syntax that I'm going to be using is called Decision Tree September 17. So I'm going to, even though today is already the 19th, but I'm going to place it also with the video lecture. That way you have it accessible in case you cannot see everything on the screen. Certain things I can enlarge, but certain things like from the notepad or when I'm in the R platform itself, I cannot, in the GUI application, I cannot make it bigger. Unless I guess I used RStudio, but I don't think that we need the RStudio for Windows. So we're trying to keep it a little bit more manageable and simple. So again, we're going to invoke the MES library and the Boston data set. And I'm just going to be copying today from the notepad. I know it's not the most conducive way of doing that, but just kind of show you, by line how the commands are being executed. So again, we're talking about these 506 cases and 27 variables. Then I'm gonna use library called gtools. And there is a function within that library that says quant cut. So for example, if I want to cut the lstat variable, then I'm gonna use that the quant stat or the quant cut rather function, and I'm gonna specify that I want basically the 4 quantiles, which are quartiles. And then when we look at that specific variable, because I'm renaming that and calling it lstat.q, meaning quartiles, you can see what the function actually did is it provided the ranges of data that fall within the first quartile, second, third, and the fourth one. So the first quartile goes, for example, from 173 to 695, and it's a closed bracket, meaning that 695, it includes the value of 695. Then we have an open bracket, 695 to 11.4. And that's an open bracket, meaning the first value is not included. Basically, like values like 696 are going to be included in the second. Now, because it gives you the levels in terms of these ranges of data, which is not the best way to read it, then basically I'm using another, and that's not something in gtools, but it's just a standard. I'm renaming these factors or these levels that pertain to these factors, like 173 to 695. And I'm renaming that as 1, second quartile, 2, third quartile, 3. Instead of looking at the values and these ranges, I'm looking at the specific quartiles, because that's going to be a little bit more conducive in terms of the interpretations once we looked at the models. And then I'm going to execute that for all of the variables. So, that's the beauty of syntax in R, that once you have it ready, it's very easy to execute it and kind of do it as a one string of commands. And then if we look at the Boston structure right now, you will notice that it will include all of these factor variables. Now, some of them, like Charles River, because that's whether or not the house bounds Charles River in Boston, which is given a factor of 1. If it doesn't, then it's given a factor of 0. That was already a dichotomous variable. And also what I did with the outcome variable, which is the median value, I divided that into 2 quantiles with a median value, separating these two, because I want to have a dichotomous basically outcome, like in logistic regression. Either the student passes or doesn't pass, or the Titanic passenger survives or doesn't survive. So likewise here, I'm either in the first quartile or quantile or in the second quantile. So that's going to be, because that's going to be an outcome variable. And it's possible to have multiple levels. Originally, I did it with a 4. I even built everything, the interpretation based on the 4 outcomes. But it gets a little bit more convoluted, and perhaps to start with, this is what we're going to be doing, looking at the 2 outcomes, and that's going to be plenty, already to do so. And also make sure that I have that, outcome variable cut as 2. Then I'm going to create another database where I don't want to be using all of these variables here that are in the Boston data set. So I'm going to create a Boston.qc2, meaning quantile cut 2 for the outcome variable. And I know that the other ones are quartiles, and bind basically by using that C command in the column, meaning bind these particular columns, and then I have only the 13 variables, including the outcome variable, as a clean data set. Now, so far, everything that we've done in terms of the predictions, when we looked at the weather report, or we looked at the Titanic data frames, was basically a prediction, judging the prediction how effective the model is, but based on the entire data set. So we train the model based on the data set, and then we applied it to the same data set. But the idea, of course, it is to test how the model under consideration, and when we say train, we train the data set because we have certain tuning parameters in machine learning language that allow us to build a more accurate model, or maybe more parsimonious model. One of these ideas was that you can designate the minimum split, so the minimum numbers of cases that are present at each split, or you can specify the number of elements that end up in the terminal nodes, which is minimum bucket, command. Or you can, and we haven't explored that yet, but you can play around with the complexity parameter, so-called CP parameter. And there is a method of choosing which, CP or complexity parameter is the best, or you can even incorporate maybe a prior structure if you want to give more emphasis to sensitivity as opposed to specificity and things of that nature. Then you can specify the priors in terms of the classification. So sensitivity, again, relates to everything that is with reference to the one category, or the success category. So for example, if I have too many false negatives, which are predicted to be 0 and actual 1, if the reference is indeed 1, if we define success as 1. It's not always defined as 1 is a success, because if it is maybe presence of a symptom, then 1 is not the desired one. So reference category is going to be 0. In rpart language, it's called R, and then you specify whether the positive value, whether it's 0 or 1. So depending how you structure that, there is a positive outcome and then the negative outcome. In some of the terminology can apply like that. So the idea is to split the data set into the train and the test data, because ultimately we want to test how the data or the model does after being adequately trained. And there are sophisticated methods of training data sets that include maybe iteration of various parameters. We're not going to get so fancy, but you basically got that idea from the minimum bucket that we used, in terms of the Titanic database. So to do that, I'm going to sample from the number of rows that are contained in that newly created Boston QC2. And I'm going to select a size of 60 of the number of rows, and that's going to be the train data. And the test data is going to be a negative of the train data. So it's going to be the remainder of the 60%, so the 40%. And then I can look at the structure of both of these. And we can see that the train data is 303 observations, and the test data is 203 for a combine of 505, 13 variables. So everything seems to be proportional, because if we do a quick computation of 303 divided by 505, that should give us 60%, and indeed it is exactly the 60%. So the computer has done it correctly. The only one thing that is very good to check is to check the proportion of the distribution of the first quantile, second quantile values with respect to the outcome variable is the same between the two data sets, the train and the test data, and we can see that they are very similar in terms of the proportions. So we know that the one model is not going to be biased. The next thing that we do before we actually apply a given model, instead of like writing in the past, we would say median value QC2 depends on And then we would list all of the 13 variables. There is a trick of the squiggly line, the tilde with the dot, or the period that means everything that follows. And we're gonna code that as a formula. So then when we execute our first model, which will use the rpart function formula, we're gonna say equals formula because we define it as the median value and then everything that follows in terms of the quantiles. The method is going to be class because all of the variables or features that we're using and the outcome variable are class type variables because we turn them into a factor. We're gonna use data, the trained data. So let's execute that command and let's see what happens. And what happens, we have basically, if we do the model QC2A, which is the first model, I call it A, we can see that we start with a root of 303 observations. 150 are correctly, so to speak, sitting in the correct bin because they're sitting in the correct bin of 1, which is I guess we're using that as a positive. It doesn't really matter which one you call it positive because it's not necessarily that the higher price is better of the house. So I guess it took it automatically as 1 being the bin that is classified as the positive value. Now, if we want to plot the tree, because it's nice, to see all of the nodes. By the way, this is the node. Then the second command is basically giving on which variable I'm splitting the root. So it's starting with the else that variable, and it's using the third and the fourth quantile. And if we split the data with respect to the median value of the price that way, then we have 161 correct classifications, 28 incorrect classification, and the predicted value is going to be 1. So to see that visually, probably the best way is to actually plot the data, and we can see this is the very first split that we discussed, which was, I guess if we minimize the graph here, it said that if you go to yes to the left where the Q stat is equal 3 or 4, it kind of overlaps here, so it's a little bit difficult to see. But if we're splitting basically the most important variable that optimizes the choice between the median value of the house that falls within the first quantile as opposed to the second quantile, is to look at the lower status population within a given neighborhood where the house is. That's the most important variable, and it's based on that importance or gain function that we discussed, where we compute the entropies. Now, how would you know at which value to split it? Again, the computer is going to go through all of the iterations, and it's going to select the one value, the split that produces the most gain in the function. So that's in essence what is happening. And the most optimal split in terms of the feature is the lower status population, and in particular, if the rooms are 3 and 4 versus 1 and 2. If you're 1 and 2, then you go to the right. If it is 3 and 4, then yeses go to the left. And we have 158 plus 3, 161 observations sitting here, because that's the number of observations that we end up with if we basically classify the response variable with respect to the number of lower status population at 3 and 4. Now, once we do that split, we can see that 133 observations are correct. and 28, because 28 plus 133 is the 161, are the correct. And in terms of the correct classification, it's 1. So it's the first quantile, and 82% of these observations are correctly specified. And all of these, the 160 is basically a 53% of the 303 variables that are sitting here at the root. So it's 153 and 150 in the second class. I expect it to be even, of course, roughly, because again, we split them artificially by using the median value and subdividing into the 2 quantiles. If the LSTAT population, so the percent of lower income population, is 1 or 2, if they're sitting in the first and second quantile, because again, we're looking at the 4 different quantiles, yeah? Then we end up with 122, 20, 142 of these observations, which constitutes 47%. And the correct classification is 2, meaning the upper quantile value for the price of the house, which makes sense, really. Yeah, it makes sense because, you know, if the proportion of lower income population is lower, then of course the price, you know, of the house is expected to be higher. Incorrect classification is 20. Second class or second quantile is the correct classification. Then another split that follows to the right, which is no. If the number of rooms is 1 and 2, yes. Then you go to the left. If the number of rooms is 2, 3, and 4, then we go to the right. So lower status income population is in the first and second quantile, meaning it's a lower concentration of lower income population. And the number of rooms is higher than falling in the first quantile, second quantile. It's a higher number of rooms because it's the 50% of observations that fall within the higher number of rooms. Then we go to the right, and these numbers at the bottom constitute 35% of the observations, 1 of 3 of which are correctly classified, and only 4 are incorrectly classified. So the particular split that we're looking at is, let me see, it's 107 that we're left with. And that's the rooms number, let me see, LSTAT, number of rooms. Yeah, here we're looking at the very last node. It's the terminal node because we have the asterisk associated. Of course, it's going to be the last one. I should have gone there right away. So it's a split that follows the LSTAT quantile, which is the third node, the 142 observations with 122 correctly classified, 20 incorrectly classified because the loss is incorrect classification of 2. And then after that split, the second split is number 7, the node number 7, which is rooms 3 and 4, where we have 107 observations, 4 incorrectly specified, and it's the second class. Now, if we go to the left, then we're using crime statistic as the determination. If we go to the right of age, we're using the nitrogen oxide levels, and then after nitrogen oxide, the criminal levels. And that's basically what we call a saturated tree because we didn't put any constraints. We basically allow the program to work itself to the lowest level of impurity that it could come up with. And we can see, even though we allowed it, the system or the rpart function to do so, we end up with not entirely pure classifications. Now, the ones that are the terminals here, classification 1, which is the first one, 123, which is node number 4. So it's 1, 2, 3, 4. This is the fourth node. We can see that it's pretty pure, but there is still about 10% of misclassified cases of houses that, if I go by LSTAT of being 3 and 4, an average age of being in the first and second quantile, I don't always expect, it's not a deterministic, it's probabilistic outcome. The outcome is not totally homogeneous, because if it was totally homogeneous, I would expect 123 cases there. But it's 110 versus 13 of misclassified. Likewise, if I follow to the right, where I have the LSTAT of 1 and 2, and then the number of rooms of 3 and 4, so both of them desire, I want number of rooms to be large in the third and the fourth quartile, and I want the lower percentage of, or a percentage of lower status population to be lower. That would dictate that the house price is more likely to be in the third or the fourth quantile, which is the second outcome. And in there, if I use these two criteria, I have only 4 misclassification out of 107. So definitely less than 5%. So I'm better at predicting, you know, the second quantile, the higher prices of the houses as opposed to the lower, based on these particular two paths that I examined. Now, anytime that you see an asterisk, that means it's a terminal node. So like this one, 14, which is this, which is number 10, node number 10, it's the terminal one. Then another one, which is 9 and 3. I'm sorry, 9 total, which is 6 and 3 is this one. And that's node 22 is this particular one. And again, each time that you see an asterisk here, that means it's a terminal node. It's not an internal node, so it's a leaf. What do we call a leaf? It's not the internal node or a parent node. So these are daughters, but the parent of these two guys is basically this one, which is an internal node, which is criminality Q equals 3 and 4. 3 and 4, and then Knox, that's the parent to the criminal split, then nitrogen oxide, and then age is a parent to nitrogen oxide. So this is basically how the models, performs. Now let's see how the model does specifically in terms of predictions, and we're gonna use the trained data and model QC2A, which is the first model, to save a data frame of predicted values from model A. So I'm gonna call it predicted train A. And then I'm gonna use a function that is coming from caret library, which is called confusion matrix, that will compare the saved data frame from the train section and use the reference in terms of the actual values. Now notice that what we intended to do is to actually compare it how it does in reference to the to the test data, because it's really critical to compare how the model does in terms of the test data. So now in terms of the train data, we'll look how the model does. Of course, I have to invoke caret library, which I didn't do. And we can see that the overall accuracy on the train data, which is the 303 cases. So it was the 141. I guess I had it somewhere here, 141. 142, 141. Okay, we can use one of these pre-coded in Excel. 141 versus 125, and then we're gonna have the off diagonals are 25 and 12. And we can see that the overall accuracy is 87%. The sensitivity is very good because it's 92. That's the positives. Anything that deals with the positive value is one value in this instance, because that's how we defined it in the confusion matrix. So it follows actually to the left. So anything associated with the numbers in the left are the true positive numbers. And then anything that has to do with specificities actually in the non-positive column, which is the second quantile. And we can see that the specificity is in particular maybe more trouble. It's 83%, still very good, but it's worse than the sensitivity and hence, worse than the overall accuracy. If we take the diagonal numbers, that's basically where we get the accuracy. So if we take 141 and 125, which are the true positives and the true negatives, and we divide it by the overall sum of these observations, it's going to be 266 divided by 303, which is that 87%. So that's basically what we did with respect to the train and the train data set. But of course, the next idea is to evaluate the model based on the test data. So I would estimate that that particular performance is going to decline. Now, the one thing that I was doing that I neglected to do actually in order to replicate the results that I see in the PowerPoint presentation was to set a seed, and I had a seed set to 1 to 3. That's basically when we sample it, randomly sample the 60% of these observations from the data frame of Boston. I want to make sure that I am always using the same number or the same random sample. So the confusion matrix that I was looking at that is already in presentation had the 130 and 140 on the diagonal. And we had it slightly different, of course, before. And because we're looking at 141 and 125, that's why I had to replicate the results here on the spot. But if I set the seed to 1 to 3, then I'm basically able to replicate the predictions in terms of what I already had in the presentation, 130, 140 on the diagonal. Not a big deal because the overall accuracy is actually pretty similar, 89.88. It's a function of random error fluctuations. So that's basically how we execute the model. We were able to create a class variables in the Boston data frame. We created a new data frame, Boston.qc, that contained all of the factor levels of the 12 predictor variables, with the exception of 2 that one of them was based on 2 quantiles, one of them on 3, one was a dichotomy like the Charles River. And the outcome variable was put in 2 quantiles based on the median value split. and we created two groups of, or two buckets of outcomes. One, which is the lower average price of houses, which is in quantile 1, and then the higher one, which is above the median value. And we're trying to come up with a model that would optimize basically the splits based on these gain or importance functions. So first, which feature, which class variable am I going to use? And then which class within each variable that I'm going to partition the data to optimize what? To optimize the classification of the cases from the parent node in the lower buckets into the daughters nodes that would optimize the homogeneity, would optimize the split into the lower and higher average house prices. So basically that's what the objective is. And even though we didn't put any constraints, any controls on the models, we didn't end up with homogeneous buckets at the bottom. Now in the next video lecture, I will incorporate a constraint, a minimum bucket, and then we'll evaluate how the model does in reference to the test data as opposed to the trained data, because we want to test the performance of the model based on the test data. So there's going to be another one in the sequence. Thank you for your attention.